questions. We have 3 people who have responded. And then we will go to the didactic, which is 2D mensuration actually today. And then Senthil will be talking about possibilities for the next 20 minutes. And then the final, we'll have a wrap up and a feedback, final 10 minutes. So let me continue. So Santosh, are you there? Oh, Santosh is not there, you said, Smita. Santosh, are you there? Would you like to tell a little bit more about? Okay, if Santosh is not there, let's go to, let's go to, Namita. Namita, are you there?
Yes, ma'am.
Yeah.
Yes, ma'am. Good evening.
Yeah, thank you for your response. Could you tell a little bit more about last week's, I think last session we had asked how you plan to use paper folding in your classroom, and then what are the different ways in which you can introduce, you usually introduce algebra in your classes. Yeah, so please go ahead, Namita.
Actually, I was not there in the last session due to fever, but
Okay.
for paper folding, I
Huh.
have whatever I could brainstorm was like, if you fold it in a symmetrical manner, like first you take a square shape origami sheet and then fold in a rectangle, then again overlapping it to form a square, and then so
Yeah,
on and so forth. You form a lot of intersecting lines in a symmetrical pattern, and you can cut also to form various patterns, and then when the lines intersect, you can identify right angles, acute angles, obtuse angles,
correct.
various kinds of angles you can introduce and ask the children to identify as well. And then the line segments are also there. Obviously, you can find the shorter ones and the longer ones, or some line segments if we like the overlapping ones also, like that. So paper folding can be, in my view, can be used in these ways. Symmetry, angles, line segments can also be introduced using another idea which I had used in my class, using drawing rangolis. So
Okay.
rangoli patterns also give us the same thing. Uh, for the introduction of algebra, uh, I generally start with a situation based question, like if we do not know something, but we are given the relationship between them. So, how are we to find the values? So, that ways. And some concrete objects, like we get some mental agility questions, like if two blue squares are added and one white yellow triangle is added and its value is this, and then similar relationships are given, so what will be the value and the yellow triangle? So these kinds of questions probably give us the reason why we have algebra in the first place. We do not know some things value, so we assume it to be x and y, to instead of taking the object in the first place, and then we assume some certain alphabets, and then we move forward to solve them using their relationships.
Yeah, yeah, yeah. Yeah, that is really nice, Namita. So thank you for sharing. We actually, Ramesh also talked about similar situation based ideas last week, and for paper folding also we talked about how we can fold, use origami and fold. Say you make maybe a boat or a frog out of origami paper, and then you open it up and you see all kinds of angles and line segments and different even polygons which the children can explore. So we did this last week. So I think when we share the PPT, then this will be similar. Yeah. Thank you so much. I think if Pushpa and Santosh are not there. Santosh, are you there? Okay, so I'll just go to my didactic and then we can come back to this. Yeah, okay. So last week, we talked about how how we can use paper folding to introduce 2D geometry to children. Different kinds of polygons and lines and points and angles can be introduced to children. And this week, we see how we can use paper folding for um, introducing mensuration to kids. So for example, over here, one of the very common properties of triangles are it's the sum of any two sides of a triangle should be greater than the third side. So this, if you just take a long strip of paper, which is equally marked, like shown on the bottom left, and we actually try to fold this into a triangle. For example, if we fold it, suppose we have fold it into a triangle where the sides are 12, 6 and 10. Okay, so the base is 12, one side is 6, the other side is 10. And we can see we can make this triangle very easily in the top right. But at the same time, the sides are length 17, 6 and 10. If the base is 17, we see that the 6 and the 10 sides can't even meet at the top. So it's very, very clear for the children that it's impossible to make a triangle unless the sum of two sides is greater than the third side. So another property of a triangle, which very common property, of course, is that the sum of the interior angles in a triangle is 180 degrees. So for this, we take a triangle and then we fold it, right? So you mark the three angles as ABC, and then you turn it around, and then you fold it, you bring down the top vertex A down so that it meets the base BC, right? And then you fold the other two angles also, B and the C, so you get a nice rectangle as shown to the bottom center. And you can see that the angles A, B, and C, they together meet at a point and they make a straight line. So basically, A plus B plus C is 180 degrees. It's very, very clear. And when we are doing like another way is when we are teaching them alternate angles and corresponding angles and alternate angles to parallel lines. So if you try to draw a line parallel to the line BC through A, to the vertex, top vertex A and AB and AC, they are two transversals. So the alternate angles have to be equal. So in that way, at the top, we can see that A plus B plus C is 180 degrees. So another very common property is the exterior angle is nothing but the sum of the interior opposite angles. And this, if you take any triangle, ask the child to draw any triangle, and we can keep it and make three copies of it. And we can rearrange this as shown at the top right in such a way that the three angles A, B, and C, they meet at a point, right? So what does this mean? It again means the same thing. And this property is nothing but the previous A plus B plus C is equal to 180 degrees. It's just putting it slightly differently. So the exterior angle C is nothing but the sum of the interior opposite angles. And now we come to properties of quadrilaterals. So here the interior sum of a quadrilateral is nothing but 360. We know this. And how can we just show it by paper? So you draw any quadrilateral and then you divide it and you cut it in such a way, in any way the child can cut it, just the four angles have to be intact. And then you can put it together. The four angles can be put together as shown on the right side, and they all meet at a point. So the sum of the four angles, interior angles, they add up to 180 degrees. So if we do this, there is no need of memorizing all the properties. Once a child does this by hand, and all this we have seen that each for any kind of triangle or for any kind of quadrilateral, this is going to hold. Because when you in a class, when you ask a child to draw a rectangle or a quadrilateral or triangle, each child is going to draw a different triangle and a different quadrilateral. So this is a common property which is going to hold for all kinds of quadrilaterals or triangles. And again, the sum of the interior angles of an n-sided polygon, right? We saw for a quadrilateral, which is nothing but 360 degrees. And what is it? And why is it 360? One other way of looking at it is a quadrilateral can be divided into two triangles. And you know that the sum of the interior angles in a triangle is 180. We just proved. So we have two triangles now. So it is 2 times 180, that is 360. And if you draw a pentagon, any pentagon, you ask the child to cut it into triangles in such a way that the triangles don't overlap. Uh, yeah, so we can cut it into 3 triangles as shown. So, and so what is the sum of the interior angles? It's going to be 360 plus another 180, right? 540. And so this goes on, right? So now we can generalize it. Ask a child if it is going to be 6 sides, it's going to be so much. If it's going to be 7 sides, what is it? So the general formula is the number of sides. Each time you have to add 180 degrees. You get one extra triangle. So it is nothing but n minus 2 times 180. And even if a child cuts up a polygon into, say, an octagon as shown below, right, into 8 triangles. So here these are triangles which are meeting at the center. So the center angles don't count, and we know that the center angles together add up to 360. So the sum of the interior angles, it's nothing but n times 180 minus 360, and we get the same formula. So this way, if a child can understand and sort of as a class, they discover the formula by themselves, nothing like it. And similarly, for the exterior angle sum, ask them to draw any polygon, right? And you extend the angles and you cut out the angles carefully and put them all together. And this adds up to 360. And this is quite amazing, irrespective of the polygon, whether it's a hexagon or a nonagon or whatever number of sides, right? The sum of the exterior angles is going to be 360. And this, if the children discover it, they find it fascinating. Why is it 360? We ask. When we look at the area and perimeter, right, it's best to start off with a square paper, right? So to understand the meaning of area, so the child can count the number of squares in any shape, and that's the area. The number of unit squares they can count, and that's the area. So if it's going to be both for regular and irregular shapes, and if it doesn't exactly come into one square, let them approximate it. Say this is half a square, this is quarter of a square. So you add up so total number of squares and get an approximate area. Approximation is always good. They learn to approximate. It's good. And then when we come to regular shapes, start off with a rectangle and let them count the number of unit squares into a rectangle, right? Initially, they'll spend time counting all the squares. And then they realize that a easier way is to just multiply the length and the breadth. And so automatically you get the formula for the area of a rectangle. That's nothing but length into breadth. And in order to differentiate between area and perimeter, this is a very nice activity. We know that, so you take unit squares again, put them together, right? So you have one unit square, the area is of course one square unit, and then the perimeter is 4, assuming the length of the unit square is 1. You put two square units together, the perimeter is going to be 2 plus 2 plus 1 plus 1, that is 6. 3 squares together, it's going to be 8. And you can continue like this. And ask them to once again generalize. And as and when we generalize, whether it is geometry or whether it's arithmetic, algebra comes in. You're going to say, if the number of squares are n, The area is nothing but n square units. That's obvious. And the perimeter is nothing but 2n plus 2, the two sides together. And this is a very nice area and perimeter challenge, and it very clearly brings about the difference between area and perimeter. So tell them, I have a fixed perimeter, like 12 units. Okay. So give them the unit squares, ask them to make as many different shapes as they can in such a way that the perimeter is a constant. It's always 12, but area can be different. And you can see all the different, on the left side, all the different shapes that you can make with different, all of them have a perimeter of 12 units if you count, but they all have different areas. And the same challenge similarly, say that the area has to be a fixed quantity, say 9 square units. And the perimeter can be different. So what are the different shapes that they can make, right? So here you use 9 of the small squares. So the area is fixed 9. And then the different kinds. And then ask them to reason out why. So if the more compact that shape is, like for example, the last 3 by 3 yellow squares we have, the perimeter is going to be the least, right? And they can understand why. And so now that the children have understood the area of a rectangle, how it came about, the rest of the different 2D shapes, they don't have to memorize the area, the formula, right? So how do you find out the area of a parallelogram? You can just cut out one edge, make it perpendicular, and if you add it to the other side, you get a rectangle from a parallelogram. And so that's why the area of a parallelogram is also based into height. And that's why the height has to be the vertical height and not the slant height. This is very clear from this activity. And then after rectangle, you start with rectangle or a square. Square and rectangle, they are similar. Then we come to parallelogram and now a triangle. So ask them to cut out any triangle, 2 copies of it, the same triangle 2 times, right? And you put it together, and depending on whether it's an obtuse angle triangle or a right angle triangle, you get either parallelograms or you get a rectangle. And since you know the area of a rectangle or a parallelogram is based into height, and we are putting 2 triangles together, so the area is nothing but half base into height. So the lesser number of formulae they have to memorize, the better it is. And this is very good for us teachers to understand this principle of area. It's called Cavalieri's principle. So this is what it states. It states that if you have 2 shapes of the same height and matching widths everywhere along that height, then the shapes have the same area. So suppose on the left, you have this kind of a it initially was a rectangle, and then you sort of shear the top, right? Shear the top. Still the area remains the same because all along, it's like adding the same amount, okay, of the same width along. And the area, whether it is on this light blue, the funny shaped on the left, as well as the rectangle, both have the area 42 because the height is 7 and the perpendicular height is 7 and the width is 6. And the same principle holds for a triangle or anything shaped like what is shown on the right. Yeah, along the same height, it's the same width. Then these two figures have the same area. And that's why, the reasons why, whether it's a right angle triangle or an obtuse angle triangle, whatever it is, it's like you're pushing the top vertex, you're just shearing it along, but the area remains the same. And this we can see very easily with the pack of cards. I think Senthil will show it next class or something like that. Yeah, I remember. Yeah, and then we come to an area of a trapezium. And again, it can be cut into 2 triangles. And one triangle has The base is A and the height is h. The other triangle has a base is b and height is h, and put them together and you get the area of a trapezium as half h into a plus b. And then you have the circle, and this is a common activity which we all should do when we are introducing a circle. That is, take a piece of string and go around any circular object with a string, measure the length of the circumference with this using the string, and then again the diameter, and this ratio is always pi. And that's an amazing activity for all children for any kind of a circle, and sort of defines a circle. And this on the right side, we get all these building toys. You know, they have these little pieces of rods. You can connect these rods. And here I could connect 22 equally shaped rods. And center, we have the same rods. So once again, we have a visual proof of that 22 by 7 is a very close approximation to pi. And we have this activity of a circle, the area of a circle, where we can cut up a circle into tiny triangles, and we approximate this as a rectangle. And so that way, the area of a circle is nothing but pi r into r, the radius, and pi r squared we get, right? And these are other two, three gifs which I found, different ways of cutting the same circle into triangles, which is very cute. And then we have our Pythagorean theorem, apparently can be proved in more than 200 different ways. But this particular proof was given by Pythagoras himself. So we take a big square and we mark sides AB, and then we say the equal sides AB, and then the hypotenuse is nothing but C. So and when we have these four equal triangles, A, B, and C, right angle triangles, they can be put together in two different ways, right? So in this, we see that A squared plus B squared is nothing but the center C squared. Yeah. And that's what I have today. Thank you. And Senthil, would you like, yeah, please.
Yeah.
Yeah.
That was pretty good, Mama. That
Thank you.
even I was also mesmerized by the Pythagoras theorem, that the way it was proved, and it's just not just one way, as you said, there are 200 ways. Yeah.
Yeah, more. Yeah.
There is a book called Pythagoras Propositions, where there are 350 ways have been documented.
Oh my. Okay.
Unless you're extremely crazy, you won't do that, I guess, to do that. And many, we also had this discussion about these Pythagorean proofs. How many of you think that Euclid would approve many such proofs? And pretty much nothing, actually, because Euclid's proofs have almost like zero assumptions, or the assumptions are undebatable sort of things. Here there could be assumptions that here is 90 degrees, because everything involves a cut and other things. So when you actually cut and move and do these things, can you really fit into that shape? Is it exactly? There are assumptions that, yeah, it could have been better, or maybe it's right, we'll agree to it. But today, as we were talking, it's also about how Euclid was just Euclid's elements were discussed, how the first four postulates, and then four postulates are very, very simple, but the fifth one is dramatically different. And without using a parallel word, how he is trying to do something in the fifth postulate. Maybe we should discuss that sometime later, I guess. Yeah. We can go on to this possibilities. So it's basically the thing is, how do we start is, it's the basic foundation for probability. But before going to probabilities, we'll look at what are all the different possibilities. And as a thing, maybe towards the end of the presentation, we'll also see how many people in this room where we are now, how many people, because we are 24, how many of us would have a common birthday? Is there a possibility that we would have a common birthday? Maybe we can check and see if that's a possibility. And it's quite crazy to believe there could be one among 24. I don't know. We'll see. Wait and watch. But this is the basic one. As the first one is like, how many different possible combinations can you choose to wear if you have 2 shirts and 3 pants? We can just start pretty simple like that. Like, or you can just have, if you want, um, there's an option of idli dosa, and then there's an option of say um, coconut chutney and tomato chutney and the sambar. Like how many different combinations you would want to have, or uh, definitely going naked is not an option. It's just with these 3 options, so whatever is there. So you can choose either the black with the gray, or black t-shirt with blue, or black t-shirt with black pant, or red with gray and red with blue. And so you end up having 2 times 3 combinations basically. So that's the basic fundamental counting principle. That's what it is. So you can to start with some 2 shirts, 2 3 pants, you can start with 1 shirt, 2 pants, 2 shirts, 2 pants, 3 shirt, three pants, and you can build on it so that children can actually understand by listing them down. Listing them down is very, very important at this stage. Yeah. The next is in a number plate, where it is that old style number plate in our country also, like where for any vehicle in Chennai would be starting with MAS for Madras city or something like that, Madras state, or something like TNM, and then 345, something like that. So if there is a number plate like this, a number plate that has 3 letters followed by 3 digits, you can see that here. The next is, if this is one of the possibilities of all the numbers that's possible, like all the different combinations, first let's understand how many different possibilities are there. If you think about it, there could be all the alphabets from A to Z for the place of U, and then again A to Z for the place of P, again A to Z for M. So it's basically the same thing as 26 possibilities for U, and then for P, and then for M, that's 26 times 26 times 26. And then for the 3 digits, again, you have 10 different combinations because it can have 0 to 9. So this is same as the previous one. It's just that how many different possibilities are available for each digits, we count it that way. So the answer would be next, as we see, it's 26 times 26 times 26 times 10 times 10 times. But we move on to the next one. If we have 4 children, and how many different possibilities are there for them to sit in 4 chairs, but differently? How many different possibilities are there? First, if that girl from the left starts, like how many possibilities would she have? She had all 4 possibilities. And the next is, if the second girl goes, then she would have only 3 chairs left. So she would get 3 more possibilities. That's 4 times 3. And then you go on to have the next child, how many possibilities? So in this example also, just like the previous one, you start with just one child. How many possibilities for one child? That's just one. Then you write 2 children, write their names, say Karthik and Arush. So Karthik gets the first chair, Arush gets the second chair. Probably they also get the chairs exchanged. So you write those combinations. If it is 3 children, 3 chairs, how would that be? If it is 4 children, 4 chairs, how would that be? List all of them down, then collect then count them, and then figure out how many were there, and see what's the logic behind this number and number of children and number of combinations. Then they will figure out, okay, I could see that if it is one child, that's just one. If it is two, that's just two. If it is three, it becomes six. If it is four, it becomes 24. Like, what is happening there? And slowly, when children see these patterns and as a sequence, what would happen to five children? So once they look at the sequence and then figure out, then they can also figure out that it is going to be factorial. It's 4 times 3 times 2 times 1. So that is something which we need to lead them to this discovering process, not just telling that as an answer quickly. Yeah. The next is very similar thing, the seating itself, like as we have been talking about low floor, high ceiling. So if a class of 5 rearrange themselves to new seating every second, how long would they really take before exhausting all different possibilities? This is something they can start counting or do writing. They can think about these things, but if 5 rearrange, they can quickly tell you how many seconds or something like that by just doing 5 factorial, 4 factorial, that's 120, 2 minutes. What happens if in the next one is, if you have much more children, like if it is 6 children, and then go on to like have 10 children, and go on to have even like 25 children. That's unbelievably, because it's extremely counterintuitive. How would you even read that number, like 492 billion years? That's really way far stretched. And that is something the class can really go high on it when they get to know that it's so much, just, and that too when you count for 1 second per change. That's mind blowing for them. The next is, this is a famous black salute. It's called the black salute, where two athletes, for the 200-meter race, it's Smith and Carlos are the black Americans, and Peter Norman is the white Australian, where they both, Smith famously told that if I win in the Olympics, they call me an American. If I do something wrong, they call me a Negro. And they were standing up for the human rights thing. And we can see that Peter Norman also wears that human rights badge with him. And it's just a pretty strong statement in the Olympics thing. And there are so many stories to look at it. You can search about this. And the thing is, like, how many possibilities are there for the 3 podium prizes in a race where 8 participants are there? How do we figure that out? Because earlier there were 4 chairs, 4 children. Now it is like 8 chairs and then 3 chairs, but 8 children, something like that. So how many different combinations do we see here? Now comes, here also you start with 3 and then move slowly to 4 and then slowly to 5 and start listing down all different options. What do you get if you have 3 children, 3 chairs? What do you get if you have 4 children, but only 3 chairs? If we can just plot them down clearly one by one, and then list them down, then we can figure out that it is actually permutations. We don't need to go and say it is NPR as a permutation thing, where it would be like, here it would be 8 times, 7 times, 6 times is the thing. But the number of ways to select so many folks from our folks would be, and put them in order is just this, r factorial by r minus w factorial. It's basically like if you have n people, and then like you need to choose only w people. And that's the thing where if you, instead of it's, the answer is actually only 8 times 7 times 6. But to get to easily cancel out from the top and the bottom, you go all the way from 8 factorial, and then below is 5 factorial. Then you cancel out 5 all the way down to 1. So it ends up as 8 times 7 times 6. That's the first introduction for the permutations they see. And this is a famous movie called 12 Angry Men. Here in this movie, this is also one of the brilliant ones to understand perspectives, how we can hold our perspectives light. So there's one boy who was accused of killing his father, and he is brought before this jury because there's not a strong evidence, but there is one jury who decides that, who sort of thinks that he may be innocent. And there are 11 other people who wants to really prove that they all thought he should be given a penalty for, he should be penalized for his death of father. And but slowly this one jury starts convincing each and every one, and all their perceptions and prejudices and everything comes out in this movie. It's a beautiful one. Here, how many possibilities are there to select a three-member jury from a pool of 12 angry men here? So it's very similar, same like three prizes with 8 people. Here, 3 members with 12 angry men, and similarly start with 3, 4, 5, and 6, and it is pretty much the same permutations itself. Or here it's the combinations, because it's the other way around. You are choosing 3 members from 12 people. So it's the other way, where it is NPR, the permutations by R factorial. That's the big difference here. Yeah, because here the difference between the previous one and this one is, there it was clearly gold, silver, and bronze. Here we are just simply saying 3 members. That's all. So here there is no one like first place, second place, third place. So if you have chosen 3, that's all. You are actually exhausting 6 different options from 1 to 3. That's the big difference here. That's combinations. And so here the combinations is, if you happen to select 1, 2, 3 as the places, and you remove, you divide that by the R factorial, then you get only, without any places, there are 3 people. That's what happens here. And the next one here, it's the scrambling of the words, the names we write. How many different possibilities are there to arrange the letters in these words, where there could be more than one letter which is repeating. And in the name Bobby, both B's in the third and fourth place, they could not be interchanged and say it's a different name. It's being in the third place or in the fourth place, it is still the same thing. So this is basically just like we started with fundamental counting principle, and then we moved to factorial, and from factorial we moved to the next step of permutations, and from permutations we moved to combinations, and now distinguishable arrangements. Here also we look at the combinations by the factorials itself of the repeating letters. So if a letter has, say, if a name has 5 letters, it's 5 factorial by, if the same name has 2 which is repeating, then by 2 factorial. Yeah, my daughter's name is Nila, and how many different ways to reorder this name? That's just because there are 12 letters, it will be 12 factorial divided by 3 letters which are repeating, 4 letters which are repeating 3 times. That's 3 factorial times 3 factorial, all the way. Yeah, this is a distinguishable arrangement on this. Now let's do this thing. So let's start typing in, because only 25 of us are there. Only if all of us participate and type in the chat box that how many of us, you can just start typing the number of the month which you were born. We'll
I'll
start.
stop sharing, Senthil.
Yes,
I'll
yes, you
stop.
can stop sharing.
Okay.
If it is September, type 9. If it is March, type 3, like that. And let's see how many are coming. And 2, 10, 8, 8, 8, 10. There are more than few, many 10 is coming, and 8, 10 and 8 are many. Is that all?
There are 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Only 12 people have typed in. All of you, please type in. This is going to be fun. Just type in your.
It will be nice for us to really understand this. It may be possible, I guess.
No, if we have 24 participants, no. So if all of us
Yeah.
type in,
How many we have so far? 12. Okay, so let's do with whatever we have now itself. So people who have born on October, type in the dates now.
yeah, some of you have sent in as a direct message. Can you just send it to everyone in the group, please?
19, 9, 8 in October, right? And let's check what's the scene with August. That was also high. Type in for August, which is the 8th month. That's 8. Only one August. There were 3, 4 August. Oh, that's close. 8, 6. And it's quite funny that the teacher who was conducting this exercise, he said, "I'm also March 15." So when the other person said, so we were a little suspicious, but he showed his passport as well. It
No,
was
no,
quite fun.
I think Senthil,
Yeah.
you should tell this to everybody. I think you told
Yeah.
this
So
to
what happens is the thing what we are trying to do is if you go into a room and then say you ask this question, how many people you need in a room to at least have one common birthday? What is the probability? And when would you bet it? If you have 10 people in the room, would you bet it? Or how many people you need to have at least 50% probability or a little more than 50% probability to have at least one common birthday? That's the question. Okay. If we ask this, start typing what is the number of people do you think? How many people you need? Start typing. If you need at least more than 50% probability, how many people you need? What do we get? 100 people? Yeah, that's one. That's an option. And 50 for more than 50% could be. And what other wild guesses we get? And this question can be approached in the other way. It's like, so children are standing outside and we say that as they enter the room, they can take a blank sheet and start writing any birthday. So once they write the birthday, they can just drop that down also and they take it inside. So or they start writing whatever birthday is not written, a new child can come and write or something like that. So they just write it and then they take it and go. The second child can take it and go. They can just say something like that. And then what's the probability that there's no common birthday? When would that happen? Say, because we say this only because in a class, all children know everyone's birthday. So only to make it random, we say this. What happens is when the first child enters the class, the child will have 100% probability. So it is one whole. But when the second child goes in, she won't have the same 100%, but only 364 by 365 into 1. That's the second person's chance. But the third person's chance is 1 into 364 by 365 into 363 by 365. So it keeps going like this. And for 20 PR, 365p20, what happens here is it becomes about it becomes 0.58856. That's 58% for 20 people. When it becomes 23 people, then it becomes something like 49%, 48. So when you have 23 people in a room, there is high chance that at least there is one common birthday in the class. There are two children who have a common birthday, two people. So in a school where there are 14 classes, and you can give this as an assignment, or anyone. I think some of the schools where the teachers are joining from, there they would have easily across all different grades. There would be easily about like 40, 50 classes also. Or even if there are 10 classes and all the classes having more than 25 children, you can check with, send the children to all these classes and ask the class teachers, is there anybody who has, are there two children who have same birthdays? You can discard the twins. Twins are ruled out. Invariably, if there are 10 classes, at least 5 classes will have a common birthday. And it's just fascinating for us to understand the probability this way. Yeah. It's just, and this topic is something, possibility and probability is not something that I would really like everyone to have a high skill to do these sums, but it is an experience for every child to go through it, and that way is good enough. Children don't need to get bogged down by NPR and NCR and factorial and all those things. So if you start with smaller number and then um, quietly include them in discovering what is a factorial, that itself is a great experience for them, because there are no prerequisites required for such a topic. It's just that basic 4 operations is good enough for this topic, so everyone can just join and enjoy this whole topic.
Yeah. Should we ask if August or October birthdays? I think maximum we have, but all haven't replied.
It could also be just people who have, there are only 2 birthdays in March. That could also be similar. We don't know. Okay. That's how the probability works, right?
Yeah.
It will be real fun if all of us, like 24 of us, are together in person. Then this would have been done easily.
Yeah, in a class together. Yeah, that's true. So shall we try? Is the 2 case people, have they joined? One is Santosh.
I think Pushpa has joined.
Okay.
She can throw some light on Miss Lata's activity response.
Yeah, Pushpa, are you there? Should I?
Yes, ma'am, I'm here.
Yeah, I think your Miss Lata's colleague, I guess, she told me that you can throw some light on the one of the activity response she gave.
Yeah, for the algebra, the way we introduced, it was very similar to what Sir did on the other day. So we just, she has just shared the same thing with you people, I believe.
Yeah.
I exactly don't know what has been shared. Yes, but
I can, 1 minute, I can share it. 1 minute, Pushpa. Just let me share the screen. Just 1 second, please. I have lost it.
It's okay, ma'am. I can just tell how we do it. It was very similar to what he did. We never introduced the terms variable, constants in the beginning itself. It's first we make children to observe the pattern, repeated patterns, non-repeating patterns. They just observe that. And then we give them some patterns where they can come up with what is a pattern, they can put it across in their own words and try to establish a mathematical language for it. Yeah, this is one of
Yeah.
the activities that we do.
Huh.
Yeah, this is at the later stages we do this.
Okay. Now, if you could just tell a concrete example, that will be nice, Pushpa.
Okay. Like for example, to begin with,
Yeah.
we give them the number patterns or shape patterns. First, we start with the shape patterns. Like for example, if I have a square,
Yeah.
okay, first picture is a square, which the second picture will have a square and then an added on square on the two sides of the square. So the children keep on that there will be third picture which will have two more squares that will be added. So every picture,
Yeah.
it started with one square and then it moved on to three square and then it moved on to, the third picture was the five squares. So they find out what is the pattern, they observe the pattern and we ask them to write down what would be the fourth picture or what would be the fifth picture, and then if this continues what would be 50th picture or 100th picture. So when they have to write down the 50th picture or the 100th picture, it becomes difficult for them. So there they understand that what is the importance of observing pattern and writing a mathematical language for it.
Okay. Okay.
So
So,
after
yeah.
that, we introduce, after once they start observing the pattern, in later classes, we will introduce them what is changing pattern, what is non-changing pattern and non-changing pattern they would have understood. So what has been that is changing, that we give them as a term called as variable. That is where we introduce them the variables and the constants.
I see. Okay. So, like when I was doing that area and perimeter, like, okay, the number of squares, it's like
Yes,
M,
yes, something very similar.
something like that, right? That's what you're
Yeah,
trying to say. Okay, okay. Yeah. Okay. Yeah, this picture is also very nice where the short forms, I think the shopkeeper to write down the orders, right?
yeah.
So suppose the customer asks for 3 tomatoes and 5 apples, he
Yeah,
uses the
same
shape.
thing.
Huh.
Yes.
Yeah.
We will have a hotel situation. We will definitely Indianize this to our context. We try to
Yes.
bring in. So two
Yeah.
idlis, one
Yeah.
dosa, three
Yeah.
pakodas means how would you write? So something like that. The short
Yeah.
forms.
Yeah. 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 That is nice.
Thank you.
Okay. Thank you. Thank you, Pushpa. Thank you so much. So by any chance, is Santosh there or?
I think Santosh hasn't attended today.
Okay. Okay. So today we finished quite early.
Bama,
Yeah,
why
yeah,
don't we
yeah.
do some sort of I think playing with numbers.
Okay, sure,
So,
sir. Yeah.
which is something which I sort of learned here. So
Okay.
now, if we, since we all would know factors of a number, say how many factors for 10? And what are those factors? Basically, how many factors for 10 is a question. So you can start typing in the chat box. How many factors do you think are there for 10?
Yeah. We're getting some answers, sir.
Yeah, that's correct. 4. How many factors for 8? Correct. Very nice. How many factors are there for 4? That's right. Can you tell a number which can have 13 factors? What would that number be? Okay, tell a number which has 5 factors and then we look at a number which has 7 factors, and later 12 has how many factors?
You can unmute yourself and talk, Lata. All of you can unmute and talk, I think.
Yeah, that's also better.
Yeah.
16 has 5 factors.
16 has 5 factors. That's correct. What will have 13 factors? Can you tell a number which has 13 factors? Yeah, 12 has 6 factors. That's right. Which number will have 13 different factors?
Twenty-four has only 8 factors. So to go
24
higher,
has only. Okay, think about this. Which numbers do you think will have odd number of factors? What makes the odd factors?
oh,
Yeah, square numbers. That's right. And
yes.
what would be a square number which will have 13 factors? You can look at 16. 144. How many factors will that have? So it's very interesting. Actually, it's something which you can work with. Okay, 13 factors you need to get. What is that number? Okay, let's see. What is that number you think will have? 16 has 5 factors. What is the number which will have 7 factors? Okay, this is one question. 128 has 7 factors. Is that right? That's right, I think.
Yeah.
No, I think it has probably 9 factors. 128 has 9 factors. We can list down that. 1 and 128 is the first 2 factors. 2 and 64, 4 factors. 3 and 32, or 4 and 32, which is 6 factors so far. And 5, 8 and 16, that's 8 factors. And
But 128 is not a square number.
not 128. I think it's 128 is not a square number. 64 and which one is? It's not 128. 128, 128, and then 2 is 64, right? And then 4. But it does not need to be a. Does it need to be a square number perfectly? Yeah, it has square number into it.
Yeah.
Which number is that? Okay, think about this. And the next question, write in the group for 13 factors, what's the number? And by the way, there are many numbers available. The thing is, what is the minimum number? Write that. And then what would be the number which might have 45 factors? And what is the relation between 45 and 13? So it's just fascinating to play with number theory itself. So I think if we can look at, so which number will have 7 factors? If you look at from 16, the next is, it has 1 and 16, 2 and 8, 4 and 4, which is 1, 16, 2, 8, and then 4, which makes 5.
I think.
If you go to, say, 32, 1, 32, 2, and but 1, 3, 5, 9, 45. Is that all? But it will have 15 also, right? In your example. So 1, 32, 2, 16, 4, 8, 32 will not come. So if it is 64, then 1, 64, 2, 32, 4, 16, and then 8. That becomes 7. For 7 factors, it is 64. For 5 factors, it is 16. For 3 factors, it is 4. I think with that clue, you can go up to what would be there for 13 factors. And similarly, did anyone arrive at 13 factors? Yeah, this is a fascinating thing for us to
I'm not sure. Is it 1024, sir? 1024?
1024 is will have 11 factors, I think,
So
not
is
13 factors.
2048?
Will have 12 factors.
4096.
That's true.
4096.
Yeah, 4096 will have 13 factors. If that is the case, what is the number which will have 45 factors?
So is it 2 to the power of 40? Is that, I mean, something relative to 2 to the power of 1, 2, and so on goes on, I believe.
Goes on what number?
Sir, it is about the square number, sir. Square numbers minus 1.
So if I say 45, 13 factors, you arrived at 2 power 12.
So it
So
is minus 1. If the
that
number
will
is
work.
n,
That will work, but is there a possibility of a smaller number than that?
I'll just try.
For 13, 4096 is the smallest. But for 45, definitely that's not smallest. That is one number. Just check this. What happens for 36? 36, how many factors are there? Find that out, and maybe you will get a clue.
$36 is an even number, Sandil. That's okay?
I know. 36
Okay.
is an even number. But how many factors does it have?
It
Okay.
has 9 factors.
It has 9 factors?
Yeah.
136, 2, 18, and then 3, 12, 4, 9, and then 6. That has 9 factors. Correct. What will be a number which will have, say, tell me another number which has 9 factors.
12, 18, 36.
12, 18, 36. So this 3, 4, that's correct. 3. What is the number which will have, say, 8 factors?
Twenty-four, 30, 40. All even numbers, sir.
24, 24 is 8 factors. How? What happens there?
24.
So 54.
54 is a possible. For 24, that's also a nice number. So for 24, you said it has 8 factors. If you do prime factorization for 24, what would you get?
It's a composite number, na, sir?
Yeah, but if you do a prime factorization, you would end up having 2 to the power of
2 cube into
3 times 3 to the power of 1.
Yeah, 2 cube into
Yeah.
3. Yes.
2
cube
cube into
into
3.
Yeah.
And what is the relation between 2 cube into 3 and 8 factors? Because there was a relation between 2 to the power 13, 2 to the power 12 and 13 factors. Similarly, what is the relation between 2 to the power 3 and 3 to the power 1, along with that to 8 factors? So similarly, if you find, say, for 8 factors, you didn't have to go till 2 to the power 7. 2 to the power 7 is really far off, but 24 is such a low number. Similarly, for 45, there is a low number. And what would that number be? That's a very interesting thing to figure out. And just playing with these different possibilities itself is one good thing, where everyone can be participative and children can just start figuring out. And this can be like a low floor, high ceiling thing also. You can start giving smaller numbers, smaller square numbers, and then ask them to find factors, and eventually give them a larger number and ask them to find the pattern to it. That will be fascinating for them. I'm so tempted to let out the answer, but I really
Don't
want
don't tell. Yeah.
yeah. Maybe the group will wait and then see, and I can
Yeah.
write down those things and then share.
Yeah.
What is the number? What is the smallest number to have 45 factors? We found for 13, that's true. And I've given enough and more clues also. So we'll see what would that be. Okay, or I'll do another thing. Okay, I'll share one more thing. So if I say an odd number, okay, like say 7, tell me 2 square numbers which have a difference of 7. Is it possible? Two square numbers.
So 4 square minus 3 square.
4 square minus 3 square. That's correct. What would be the number? What would be the 2 squares whose difference would be, say, 11?
So 25 and 36.
Yeah.
25, 36. That's correct. What are the squares for, say, 19?
And 9 square and 10 square.
Yeah, that's correct. That works. What are the squares for 15?
So I
8
think
square
the
minus 7
difference
square.
between the squares it will be the same as the sum of the numbers, right?
But tell me what's the squares for the 15? It will be interesting.
Sir, 64 minus 49, 8 square minus 7 square.
That's true. But why aren't we thinking about 16 minus 1? which is 4 square minus 1 square. That's the easiest to get it, no?
I think
But where
you're thinking of consecutive numbers, but
It's
you
not
Yeah.
consecutive, no?
consecutive.
for 15, it's also 16 minus 1, no? That's the easiest. And we
just
left
thought
it
of
and then we went to
consecutive.
64 minus 49, which is also correct. I'm not denying that. So for some numbers, there are more than one solution. Why is it like that? What will be the solution for 63? What are the different squares which would have a difference of
8.
63? 8 and 1, as I said, yes. You could look at 1
Yes.
first.
I think
And
31 square and
and
32
then which one?
31 square and 32 square.
That's also correct. 2. Is there anything more? Are there more than this?
8 and 1, sir.
8 and 1 is 1. 32 and 33 is another one. And are there any more?
A squared minus B squared is A plus B into A minus B.
That's true, but what with the algebra? But the thing is, if you start
if you take
writing
consecutive
down the
numbers, the difference
odd
is 1.
numbers, okay, this could be an activity. Write down the odd numbers from 1 to 50, and then start listing down the difference of the squares and how many different possibilities are there. List down them, and also the question could be, how many solutions are possible for a number, for a given number? For 63, how many different solutions are possible? If it is 49, how many different solutions? If it is 45, how many different possible? And of the different possibilities, what is the smallest? Squares. And it will be nice to see. Yeah, these are some things where you can play so much in number theory, and there's so much wonder in the numbers, and there's always a pattern to it, and yeah, it's just fascinating. So once you post the answers to these, I'll share the answers.
Sir,
Yeah.
sir, when we take these consecutive odd numbers and we take the squares, difference of the squares, we are always getting the multiples of 8. 8, 16, 24, 32, and so on.
That is also the power of 2.
Yes. Again, yes. 2 cube, 2 to the power 4.
Yes,
Yes.
2 cube. Yes, it goes on.
But 24, I have doubt.
But Bama, children find out without using the algebra.
Ah, okay.
They don't use it at all, and they would still find it.
Yeah.
They have a joy of finding these things, and as you are introducing the square numbers itself,
Yeah.
these things can play around, and eventually it comes down to that formula. Yeah.
And another thing, Sendil, because these are squares in geometry, if you draw the squares and remove the squares, and you get patterns which can be rearranged. So that is another way to prove these things, which is very beautiful.
That's true.
Because yeah. So these things, like just by moving the squares around, you make a 3 by 3 square, 4 by 4 square, and you move it around, and you subtract and things like that, you get very beautiful patterns.
True, very
So
true.
that is another thing which is very nice. Yeah, that is true. So we can find all these interconnections, no? So nice.
Yeah, and these things can actually be in our class, as we are doing some topics in grade 5 is an ultimate time for these things, where we have introduced patterns and all those things, especially the previous one where you find the numbers itself. Without them knowing the exponents itself, they can still play around with these things. It's just that number of twos which are getting multiplied, and
Correct.
so that way they can still play. You don't need to worry about the exponents. And for 5th grade, just the joy of numbers is just fascinating. Yeah.
Very nice. These all were in your workshop, is it?
Yeah.
There are so many.
Yeah, there were this other thing is the Goldbach's theorem also, Goldbach's conjecture.
Okay.
So, any even number can be expressed as the sum of two prime numbers. Any even number. But this is not a theorem which is proven false. So it is still a conjecture.
I see.
It is, so this thing can be brought to the class and told that there are many very big mathematicians in the world. They haven't proved this as a wrong thing. If you get to prove, you would become a mathematician. And they would just go like, wow, that's an opportunity for me. And they would start working on it. And that kind of a feeling is so important to be in the class.
Yeah.
And
But the number 1 plus 3 or
yeah.
1 plus, sorry, doesn't hold good here.
So prime, you don't include 1 as a prime.
Yeah, 1, yeah, sorry, yeah.
So we do this in our school, sir. In grade 4, when they are learning, introduced first time for the prime numbers. This is an exploratory activity which we do, and they come up with their own. They represent the same number in terms of the two prime numbers. We do this.
True. Yeah. No, I think it's a fascinating thing to do such activities, and some could have more than two primes things, and so
that's true, sir.
It's very nice activity.
Yeah. And even prime differences also can be there. Any composite number can be expressed as a difference of two prime numbers, though they are not proven, but still they can explore it.
Yeah, yeah, that's also true.
So any more doubts in the two problems which Senthil has given us today, you can ask so that you can put the answers in the WhatsApp group. We can continue the discussion.
So any number when you add, any prime number when you add to 2, I mean, you don't get a odd even number. I mean, sorry, any odd prime number. Usually you have prime numbers as odd number except 2.
Correct.
So automatically when you add any number, prime number to 2, the conjecture is false. So it's not always true.
It's any two prime numbers.
Yeah.
Not 2. Any two prime numbers like 5 and 7. They say
okay, fine.
One number can be represented by adding any two prime numbers.
Fine. Okay, sir.
Say if it is 20, it could be 3 and 17, 13 and 7, possible. So if it is 40, you will still have one set of prime number which you can add and then make it 40. There is no irrespective of any even number. You can't find any even number. That's the conjunction. But as you say, if you add any two prime numbers, you get an even number. But you can find an even number. Can you find an even number which cannot be added by two primes? That's the question. Yeah. Yeah, but the other two puzzles are the one where you find a minimum number which will have 45 factors. And the other thing is how many different square number differences are there for 63? You said 2. Is there a third one? Or is there a fourth one? And similarly, how many different possibilities are there for any number? And how do you find that? Yeah. Those are the two questions. I think with that, we can call it.
Yeah.
Yeah, I think the time's up. So thank you, Senthil sir and Bama ma'am, for hosting the session. It was wonderful. Thank you all for joining the session. You may share your feedback too. I'll send it across. I think we can, with this, we can end the session. Thank you all.
Thank you. Thank you so much. Thank you.
Thank you so much.